Last episode, we built the loss, a single number for how wrong the model is, and a smooth bowl shaped surface we want to get to the bottom of. But a compass only tells you which way is bad, it doesn't move you. Today, we answer the question that drives all of machine learning. Given the loss, how does the network actually change its weights to make it smaller? This is gradient descent. Here's our bowl again. The horizontal direction is a weight we can change. The height is the loss. Right now, the model's weights put us up here on the wall, high loss. We want to get down there to the bottom where the loss is smallest. The catch, the network can't see the whole bowl. It's standing at one point in the dark. All it can feel is the ground right under its feet. And the ground right under its feet is exactly the slope. At any single point on the curve, there's a steepness, how sharply the loss is rising or falling if you nudge the weight. That slope is something we can compute directly with calculus. It's the derivative of the loss, and remarkably, that one local number is enough to know which way to step. Here's the trick. If the slope is positive, the loss rises as you go right, then downhill is to the left. If the slope is negative, loss falls as you go right, then downhill is to the right. So in both cases, you step in the direction opposite the slope, follow the slope downhill, and you move toward lower loss. Every single time. Real models don't have one weight, they have millions. So instead of a single slope, we get a gradient, a vector with one slope for every weight at once. The gradient points in the direction of steepest increase, straight uphill, and our move is simple. Take that arrow and go the exact opposite way, downhill in a million dimensions at the same time. That whole idea fits in one line, the update rule. The new weights, theta, equal the old weights minus the learning rate, eta times the gradient of the loss. Read it plainly, take the gradient, scale it down, and subtract it from your weights. The minus sign is what turns uphill into downhill. Apply this once and the loss drops a little. Apply it thousands of times and the model learns. That little eta, the learning rate, is the most important dial in all of deep learning. It sets how big a step you take each time. The gradient tells you which way to go. The learning rate decides how far. Get it right and training is fast and stable. Get it wrong and everything falls apart. In one of two ways, set the learning rate too small and you crawl, taking thousands of tiny steps, training forever to get anywhere. Set it too big and you overshoot the bottom entirely, bouncing from wall to wall, the loss exploding instead of shrinking. The art is finding the step size that's just right, big enough to be fast, small enough to stay stable. Now watch it run. Seen from above, the bowl becomes a set of contour rings like a topographic map. We start out on the edge, high loss. Each step we read the gradient and move against it, and the path spirals inward, ring by ring toward the center. That center is the minimum, that's gradient descent, doing its one job over and over. So the whole algorithm is just a loop. Compute the gradient at where you are, take one step against it, scale by the learning rate, then do it again from the new spot. Each pass nudges the weights a little closer to good. There's no magic, no sudden insight, just this patient loop, repeated until the loss stops falling. Now, the honest part, that perfect bowl was a lie I told you to build intuition. Real loss surfaces with millions of weights are wild and bumpy, full of local minima, little dips that aren't the true bottom. Gradient descent can get stuck in one. But here's the surprise from practice. In very high dimensions, most of these dips are good enough. You rarely need the perfect minimum, just a low one. One more choice. How much data do you use to compute each gradient? Use the entire dataset every step. That's batch gradient descent. Smooth but slow. Use just one example at a time. Stochastic, fast and noisy, jittering toward the goal. Or use a small handful, a mini batch. That middle path is what everyone actually uses, most of the speed, enough of the stability. And this is what it looks like from the outside. The training curve. Loss on the vertical axis, time on the horizontal. As gradient descent runs, that line falls steeply at first, then leveling off as the model approaches the bottom of the bowl. This curve, sliding downward, is the single most watched graph in all of machine learning. It's the model learning in real time. So that's gradient descent. Feel the slope, step against it, repeat. It's how every neural network on Earth actually learns. But we skipped one enormous question. To take a step, you need the gradient, the slope for every one of those millions of weights. How on earth do you compute all of them efficiently? That's the most elegant idea in the whole field. And it's next, backpropagation. See you there.